Reliability of systems. This is the third film about reliability, unreliability and failure rates. And when we have a complete system, it's usually and always made up of subsystems. And we have to be able to calculate the overall MTBF and failure rate of systems when they are made up of subsystems. Such systems have dependencies. So you have something called serial dependencies, and you have something called parallel dependencies. Serial dependencies means that for the whole system to work, each and every subsystem have to work independently. For a parallel system, you have that if one subsystem fails, it doesn't matter, because the system as a whole will still work. So one example of here where you have the serial dependencies, that would be, for example, a torch, lommelykt på norsk. If you have a torch, it's made up of a light bulb, batteries, chassis, a switch and some wires. If any of those elements fail, the system as a whole will fail. So if the light bulb fails in a torch, the whole torch will fail. And if the batteries fail, the whole system will fail. And if the wires, the switch and the chassis fails, the whole system will fail. For parallel dependencies, it's very easy to think about an airplane. For example, as basic things as the pilot and the co-pilot. What if the pilot should go unconscious during flight? Well, it doesn't matter, because you still have the co-pilot which can fly the plane. So you have a parallel system dependency. The parallel system dependency is named redundancy because you have redundant system elements, overflødig in Norwegian. For serial dependencies, you have so-called single points of failures. So for the airplane system that I mentioned earlier, of course you have a mix of the two. You have both serial dependencies and parallel dependencies when you calculate the overall MTBF and failure rate of the plane. One example of the parallel elements were, of course, the pilot, and maybe you know that most planes, if they have two engines, they can actually fly and land with one engine. So that would also be a parallel dependency. But what about the wing? What if one wing falls off? Well, that would be a serial dependency, because the whole plane would fail if one wing were to fall off and fail. So how do we calculate the overall MTBF of such systems? Let's start with the serial systems, and let's go with this example here where you have system 1, which has 1 fail per year. 9 failures per year. This one has 2 failures per year, and this one has 5 failures per year. The system as a whole would then have 9 plus 2 plus 5, 16 fails per year. That's the system as a whole. And that is actually the sum of the failure rates. So the overall failure rate is the sum of the individual failure rates for such systems. Now, the mean time to failure, or mean time between failures, is the inverse of the failure rate. So the MTTF overall, the inverse of that is the inverse of each and every individual failure MTTF. Or indeed, the overall MTBF is the inverse of that is the sum of the individual inverse MTBFs. And that is, as I mentioned, a result of the individual failure rates. What about parallel systems? Well, parallel systems, they have in order to analyze that, we need to find also the mean downtime for the individual elements. Let's say the system 1 here has 9 fails per year, but it has the mean downtime of 1 day. And that is has a parallel relation to another system, which has 2 fails per year and a mean downtime of 4 days. Well, this system as a whole has 2 possible ways to fail. Either system 1 is already down while system 2 fails, or system 2 is already down when system number 1 fails. So that would mean, for the first case, if system 2 is down, it takes 4 days, right? You have 4 days, and during those 4 days, the first system must fail. So, system 1 fails while system 2 is down, or system 2 fails while system 1 is down. So, the overall failure rate would be the failure rate of system 1 while system 2 is down. And system 2 is down according to the failure rate multiplied by the downtime it takes. Or system 2 is down, goes down while system 1 is already down. And of course you can convert the failure rates lambda to the mean time between failures, MTBF. So that would be the lambda 1, the lambda 2, mean downtime 1, and so on. So all in all, the overall MTBF is, or the overall lambda is the sum of mean downtimes over the product of MTBFs. And the MTBF, of course, is the inverse of the lambda. Now, usually this calculation is much easier because, of course, you have similar systems with similar failure rates and similar downtimes. Like, for example, in a plane with 2 engines, you would have similar failure rates and similar downtimes for the 2. Now, if that is the case, then you would have 2 mdt over MTBF squared. So it's a bit easier to calculate that. And the mean downtime for such systems, that would be system downtime. That would be the mean downtime of system 1 over the lambda. So that would be the overall downtime of system 1 plus the overall downtime of system 2 divided by the probability that both of them, or either one of them is down. So it's lambda 1 plus lambda 2. So that would be the mean downtime. And here's an example that you can go through on your own. So what do you do if you have more than 2 elements in parallel? Well, actually that's not very common, because you have like for the pilot example you have 2. For another example with a server with 2 disks mirroring each other, well, that would be 2. But in some cases you have more than 2. Well, then you have to calculate 2 and 2. And then find a new MTBF for those pairs, and then you combine those 2 pairs. And of course, if you have 3, 1, 2, 3, you find the overall MTBF for that one. And then you take these 2 and find an overall MTBF and make and 2 in order to find the final answer. Next slide shows an example with a server, which will be, you can study here on the slide, or you can follow in the classroom.